So picking up with problem number 4, two particles of masses m sub 1 and m sub 2 interact through the potential. V of r equals negative k over r plus beta over r squared, where r equals the magnitude of r sub 1 minus r sub 2, where k is greater than 0 and beta is greater than 0. Part A, reduce the problem to an effective one-body problem. Part B, derive the effective potential. Part C, find the conditions for circular orbits. And Part D, determine the angular frequency of small radial oscillations about a stable circular orbit. Part E, state whether the orbits are generally closed. So we have a two-body problem. For Part A, reduction to an effective one-body problem, we're going to define the center of mass coordinate r equals m sub 1 r sub 1 plus m sub 2 r sub 2 over the sum of m sub 1 m sub 2. And the relative coordinate r equals r sub 1 minus r sub 2. Also define the mass m equals m sub 1 plus m sub 2, and mu equals m sub 1 m sub 2 divided by m sub 1 plus m sub 2. So the individual position vectors can be written as r sub 1 equals capital R plus m sub 2 over capital M R. R sub 2 equals capital R minus m sub 1 over capital M R. R sub 1 dot equals capital R dot plus m sub 2 over capital M R. And R sub 2 dot equals capital R dot minus m sub 1 over M R dot. So the total kinetic energy is T equals 1/2 m sub 1 r sub 1 dot squared plus 1/2 m sub 2 r sub 2 dot squared. And substitution gives the standard separation. And T equals 1/2 m r capital R dot squared plus 1/2 mu r dot squared minus V of r. And since the potential depends only on the relative distance, the center of mass moves freely. M r double dot equals 0, and thus the non-trivial dynamics reduced to a fictitious particle of reduced mass mu, moving in the central potential V of r equals negative k over r plus beta over r squared. So what we get here is the relative motion Lagrangian is L sub REL equals 1/2 mu r dot squared plus k over r minus beta over r squared. Okay, moving along to part B. So part B, effective potential. Because the force is central, angular momentum is conserved, and L equals r cross mu r dot, and the motion therefore lies in a plane. And in the plane polar coordinates, r dot squared equals r dot squared plus r dot squared phi dot squared. So L sub REL equals 1/2 mu times this quantity, r dot squared plus r squared phi dot squared plus k over r minus beta over r squared. And the coordinate phi is cyclic, so p sub phi equals a partial derivative of L with respect to phi dot equals mu r squared phi dot. So let the conserved angular momentum magnitude be L. L equals mu r squared phi dot. So phi dot is going to equal L over mu r squared. Energy of the relative motion is E equals 1/2 mu r dot squared plus 1/2 mu r squared phi dot squared plus V of r. So using the angular momentum conservation, 1/2 mu r squared phi dot squared equals L squared over 2 mu r squared. So E is going to equal 1/2 mu r dot squared plus U sub EFF of r. And that is where U sub EFF of r equals L squared over 2 mu r squared minus k over r plus beta over r squared. And therefore, U sub EFF of r equals negative k over r plus 1 over r squared times the quantity L squared over 2 mu plus beta. And furthermore, here it is useful to define C equals L squared over 2 mu plus beta. Then U sub EFF of r equals C over r squared minus k over r, because beta is greater than 0. And following that, then C is greater than 0. Okay, moving along to part C. So part C, we have the conditions for circular orbits. So here, A circular orbit of radius r naught requires r equals 0, r dot equals 0, r double dot. So I'm sorry, a circular orbit of radius r naught requires r dot equals 0 and r double dot equals 0. And equivalently, r naught must be an extremum of the effective potential, d u sub EFF dr, r equals r naught is equal to 0. So du sub EFF dr equals negative 2c over r cubed plus k over r squared. So negative 2c over r naught cubed plus k over r naught squared equals 0. Multiplying through by r naught cubed, and we're going to get negative 2c plus k r naught equals 0. So k r naught equals 2c, and since 2c is L squared over mu plus 2 beta, we could say the circular orbit radius is r naught equals 1 over k times the quantity L squared over mu plus 2 beta. So equivalently, k r naught equals L squared over mu plus 2 beta. Solving for the angular momentum, L squared equals mu times the quantity k r naught minus 2 beta. And for a non-zero circular orbit with real angular momentum, k r naught is greater than 2 beta is going to be required. So for a fixed non-zero L, this condition is automatically satisfied by the expression for r naught. And stability of the circular orbit, we differentiate the effective potential again. So here it's second derivative of u sub EFF with respect to r equals 6c over r to the fourth minus 2k over r cubed. And at the circular orbit, k r naught equals 2c. K equals 2c over r naught. So therefore, we could say u sub EFF double prime of r naught equals 6c over r naught to the fourth minus 2 over r naught cubed times the quantity 2c over r naught. So simplifying that, u sub EFF double prime of r naught, that's going to be 6c minus 4c over r naught to the fourth, and that's going to equal 2c over r naught to the fourth. And since c is greater than 0 and v sub EFF double prime of r naught is greater than 0, therefore, we could say that the circular orbit is stable, and every circular orbit allowed by the parameters is stable. And using 2c equals k r naught, u sub EFF double prime of r naught, that's going to equal k over r naught cubed. So that's for part C. Now moving along to part D. So part D, we have the angular frequency of small radial oscillations. We'll let the radial coordinate be slightly displaced from the circular orbit. R of t equals r naught plus eta of t, where the magnitude of eta is much less than r naught. Okay, so expand the effective potential around r naught. U sub EFF r naught plus eta, that's approximately u sub EFF r naught plus 1/2 u sub EFF double prime r naught eta squared. So, and this is because u sub EFF prime of r naught equals 0. So the radial equation becomes mu eta double dot plus u sub EFF double prime r naught eta equals 0. And this is simple harmonic motion with radial frequency omega sub r, where omega sub r squared equals u sub EFF double prime of r naught over mu. So using u sub EFF double prime r naught equals k over r naught cubed, we obtain omega sub r squared equals k over mu r naught cubed, and therefore omega sub r equals the square root of k over mu r naught cubed. So using the circular orbit relation, k r naught equals a squared over mu plus 2 beta, and we could write the following: omega sub r squared equals L squared plus 2 mu beta over u squared r naught to the fourth. So omega sub r equals the square root of L squared plus 2 mu beta over mu r naught squared. And comparison with orbital angular frequency, the azimuthal angular frequency of the circular orbit is going to be omega sub phi equals phi naught dot equals L over mu r naught squared. So omega sub r squared over omega sub phi squared equals L squared plus 2 mu beta over L squared. And since beta is greater than 0, omega sub r is greater than omega sub phi. And for beta equals 0, the Kepler result is recovered, and omega sub r equals omega sub phi. Okay, and now moving along into part E. So part E, are the orbits generally closed? So what we want to do here, derive the orbit equation. So let u of phi equal 1 over r. For a central force, Benet's equation is the second derivative of u with respect to phi, plus u equals negative mu over L squared u squared f of 1 over u. So the force is F of r equals negative dv dr, and since V of r equals negative k over r plus beta over r squared, then dv dr equals k over r squared minus 2 beta over r cubed. So for F of r equals negative k over r squared plus 2 beta over r cubed, with r equals 1 over u, f of 1 over u equals negative k u squared plus 2 beta u cubed. We substitute into Benet's equation, u double prime plus u equals mu over L squared u squared times that quantity negative k u squared plus 2 beta u cubed. So u double prime plus u equals uk over L squared minus 2 mu beta over L squared u, and then u double prime plus quantity 1 plus 2 mu beta over L squared times u equals mu k over L squared. So we define now nu equals square root of 1 plus 2 mu beta over L squared. Then u double prime plus nu squared u equals mu k over L squared. So the solution is u of phi equals uk over L squared nu squared, bracket 1 plus e cosine here of this nu times the quantity inside that phi minus phi naught, close parentheses, cosine of this whole thing, and then close bracket. So because L squared nu squared equals L squared plus 2 mu beta, this becomes 1 over r equals mu k over L squared plus 2 mu beta times this quantity 1 plus e cosine nu times that quantity phi minus phi naught, and then close bracket. Now building on that for nu, that equals the square root of 1 plus 2 mu beta over L squared, and the radial coordinate repeats when the cosine argument increases by 2 pi. Therefore, the angular separation successive periapses is delta nu sub apsis equals 2 pi over nu, and then we have 2 pi over the square root of 1 plus 2 mu beta divided by L squared. And for the orbit to close after a finite number of revolutions, nu must be rational, so nu belongs to the rational numbers, and for generic values of b, mu, and L, this ratio is irrational. So the orbits are generally not closed, and instead the orbital precesses. So since beta is greater than 0, we have nu is greater than 1. So the apsidal angle is less than 2 pi. The periapsis shift relative to 1 full 2 pi revolution is delta phi equals 2 pi over nu minus 2 pi, and for beta is greater than 0, this happens to be negative. So that corresponds to the retrograde apsidal precession under this convention. Okay, so that's all for this problem. Thank you very much, and have a great day.